This is Math 31, which is an introduction to calculus. This will be the last lesson we'll do in Chapter 1, which is looking at limits and rates of change. Section 1.7 looks at infinite series, which is something you learned about in grade 11 in Math 20-1. So we skipped that section for Math 31. Here you can see a warm-up question. I'd like you to do this question and then restart the video once you have an answer for number 1. Well, as you can see, I put a grid here because that's how I'm going to think through this question. And so if I have a function that's 1 over n as n approaches infinity, it's probably easier for me to think of the n as an x. So what if I had 1 over x as x approaches infinity? Well, what does the graph look like? Well, the graph of 1 over x, it's undefined when this denominator is 0, which means that I will have a vertical asymptote along the y-axis. And since my numerator is lower degree than my denominator, I'll also have a horizontal I should say a horizontal asymptote there. And then we'll get that type of curve that we've seen before. It's actually called a hyperbola, where our graph will be close to the asymptote here, and then it's going to curve in and then approach the asymptote as it goes down here, and that looks pretty bad, but I'll live with that for today. That's me drawing with a tablet. Same thing over here, my graph will come down along the asymptote and then approach this horizontal asymptote in this direction. So pretty scary looking graph. I wouldn't have accepted that in Math 30-1, but that's the best I can do with this tablet. So here I'm looking at, as my variable approaches infinity, what happens? Well, as my function approaches infinity, my y values are getting closer and closer to 0. So, oh yeah, it's getting closer and closer to that asymptote. So this limit is equal to 0. Now what I have in the box over here is saying, well, it doesn't matter what exponent I have with my n, it's still going to be approaching 0 if my n value approaches infinity. I get 1 over a huge number, no matter what that exponent is, as long as it's positive. And so 1 over huge is wee tiny. So as n approaches infinity, n to the exponent r approaches infinity faster, and so 1 over that approaches 0. Well, that's going to be useful as we get into today's questions. So suppose we have a sequence with a general term Tn is equal to n over 1 plus, and I should say 1 minus 2n. And if we want to find the first 6 terms of the sequence, then I could set up a table like this, where I have my n values, and I want my first 6 terms, so n will be 1 through 6, and Tn will be the value that I get when I replace each of these n's with a 1, and then a 2, and then a 3, and then a 4, and then a 5, and then a 6. Well, why don't you pause the video, complete this table, and then restart the video when you're ready to have a look at how my table compares with yours, and we'll use that to help us as we look at number 3. There you go. Those are my term values. And as we look down this list of term values, what does it look like our term value is approaching? So as our n value gets bigger, we only went as far as 6, but what is our term value approaching? So we have 4/7, we have 5/9, we have 6/11, and all of these are negative, so we'd have 7/13, and then 8/15. So all of these are getting closer and closer to -1/2. So notice if I was to continue down here, and so I went as far as 8, and I said if this was 8, then my numerator would be 8, and I'd have 15, it's negative. 8/15, well, 8/16 is a half. 8/15 is a little bit bigger than a half, but as I continue going down, it looks like this is getting closer and closer to a value of negative 1/2? Well, here in number 3, we're asked to determine the limit of the sequence. In other words, what is it going to get closer and closer to? Well, here I've suggested, I think it's probably negative 1/2. So let's look at how we could do this algebraically instead of just crunching through a table like that. So I would do the limit as n approaches infinity. So the limit of the sequence, we're assuming it's an infinite sequence, so it's going to go on and on forever. And here's our general term. Well, let's pause and think about this for a moment. As n approaches infinity, suppose instead I didn't have n's, but I thought in terms of x's, and I had some function y is equal to x over 1 minus 2x. And suppose I was to ask you, what is the horizontal asymptote? Well, from Math 30-1, what we did was we looked at this highest degree term in the numerator and this highest degree term in the denominator, and we said if we find the ratio of those terms, that'll give us the horizontal asymptote. So the x's would cancel out, so x divided by negative 2x, the x's cancel, and this would be approaching a negative 1/2. Oh, that's kind of what we were saying down here. So as we're looking for the limit as n approaches infinity, essentially we're looking for the horizontal asymptote on the right side of our graph. Now all the functions we looked at in 30-1, we had the same horizontal asymptote on the right and left. And most of the time in this course we'll see that as well, but there are times it could be different. We'll get into that in chapter 5. But this strategy that we used here in Math 30-1 is great. It always works, but it's really not mathematically rigorous. We're just reasoning it through to say, oh yeah, I found this shortcut that's always going to work. Well, the shortcut is great, but not good enough for this course. So I'm going to throw this away for the moment, and we'll look at a different strategy. Suppose I was to take this general term and multiply both the numerator and denominator by 1 over n. Why would I want to do that? Well, observe what happens. If I multiply n times 1 over n, I get this 1. If I multiply this 1 times 1 over n, I get 1 over n. And negative 2n times 1 over n gives me a negative 2. Well, how is that useful, you ask? Well, I'm glad you asked that question. Because look at this term that I have here. As n approaches infinity, what does 1 over n approach? Well, this was our warm-up question. This term approaches 0. Since this approaches 0, what am I left with? I'm left with 1 over negative 2. As n approaches infinity, 1 over n goes to 0, so that term ends up disappearing. And so that's how we get the negative 1/2, which we already knew, but this is a more mathematically rigorous or precise or clear way of showing why that's happening. So I would like you to do these two questions, similar to the two that we just did. We'll find the first 6 terms of the sequence, and then use that same strategy that we used in number 3 to determine the limit of the sequence. So I'll have you pause the video here and then restart once you've finished these two questions. There we have number 4. As I have my first 6 terms, I can see that my term value is increasing. What's it approaching? I don't know. I don't have enough terms. I would need to add more terms to get a clearer picture of what this is approaching as its term value. In other words, the limit of the sequence, I can't tell just from these 6 terms. I need more. So let's go through the process that we did in question number 3. I have 3n over n plus 9, the limit as n approaches infinity, and I'm going to multiply numerator and denominator by 1 over n. In the numerator, the n's cancel. I'm left with a 3. In the denominator, this n will cancel, leaving me a 1. This 9 times the 1 over n gives me 9 over n. And just like 1 over n goes to 0, as n approaches infinity. 9 over n will go to 0. It'll take a little bit more time because of the 9 in the numerator, but infinity is so powerful, it's going to take this to 0. And I end up with just 3 over 1, which gives me 3. Well, let's look at some more complex general terms. In question number 6, we want to find this limit if it exists. Now, using the strategy that we had from Math 30-1, we can already look and know our answer. So let's just think about that as my n approaches infinity. I look at my highest degree term, my highest degree term. 10 divided by 2 is 5. N to the fifth divided by n to the fifth, they cancel out. So I'm expecting the limit of this function as n approaches infinity should be 5. Now here's the strategy that we're going to use. In the previous questions, we multiplied numerator denominator by 1 over n. This time, I'm going to multiply by 1 over n to the fifth. Why? It's because the largest exponent that I have, particularly in the denominator, is a 5. So that's how I'm deciding this should be a 5 and this should be a 5. Why don't I look at the numerator? Well, I'll talk about that when we do number 7, if I remember. So I multiply numerator denominator by this highest degree variable, 1 over that, in the numerator denominator. So the highest degree term that's in the denominator, that variable to the exponent, that's what I'm multiplying the reciprocal into the numerator and denominator. When I multiply that out, here's what I'm going to see. So this 10n to the fifth times 1 over n to the fifth, the n to the fifths cancel out completely. N squared times 1 over n to the fifth gives me this 1 over n cubed. And 9 times 1 over n to the fifth gives me 9 over n to the fifth. Similar stuff happens in the denominator. And as we looked at this property that we put in the box on the first page, it doesn't matter what this exponent is, that r value, as long as it's positive. If n is approaching infinity, 1 over n to some exponent is going to approach 0. So each of these terms where we have an n in the denominator is going to go to 0. It goes to 0, goes to 0, goes to 0. What am I left with? 10 over 2. What does 10 over 2 reduce to? It reduces to 5. And there we go. Number 7. Well, here I said that I would talk about what would happen if I was to use this highest degree term in the numerator. So don't write this down, but I'm going to show you what happens if I was to use that 1 over n. 1 over n to the fifth, I should say. So if I was to multiply the numerator by 1 over n to the fifth and the denominator by 1 over n to the fifth, what would happen? Well, we'd still have this limit as n approaches infinity. Here, 10n to the fifth times 1 over n to the fifth gives me just 10. And then I'll have the plus 1 over n cubed plus 9 over n to the fifth. In my denominator, n to the fourth times 1 over n to the fifth gives me 1 over n. And then 7 times n cubed, that'll give me a 7 over n squared minus 1 over n to the fourth. So what's happening to each of these terms? Well, the 10 stays. This goes to 0. 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 So I get 10 over 0. Well, 10 over 0 is infinity. Or is it negative infinity? Well, there's the problem. we can't tell if our denominator is going to zero. Is it going to zero from the negative side, or is it going to zero from the positive side? We have a problem. We can't tell if this limit doesn't exist and is going to positive infinity, or the limit doesn't exist and is going to negative infinity. So we've hit a problem. To solve this problem, instead of multiplying numerator and denominator by 1 over n to the fifth, we will multiply it by, sometimes smart is not as smart as I wish. Here we go. We're going to multiply by 1 over n to the fourth, the highest degree term in the denominator. What happens when we do that? Well, now we have a 10n in the numerator, and the 1 over n squared, 9 over n to the fourth, and the stuff in the denominator, but we have a term in the denominator that has no variables. So while each of these terms goes to 0, I'm left with this. So I'm looking at the limit as n approaches infinity of 10n. Well, n is approaching a positive infinity, so 10 times a positive will give me a positive, which means my limit is approaching infinity. It doesn't exist, but I know which infinity it's approaching. So that's why we use this strategy. For number 7, we look at the highest degree term in the denominator, and we use that when we are multiplying top and bottom by the reciprocal. So here is our typical rule, and the rule that I'm expecting you to use showing the process. We'll multiply numerator denominator by 1 over n to the r, where n to the r is the highest degree term in the denominator. Notice we ignore the coefficient, so we just use the n to the r part. The shortcut, which is what we learned in Math 30-1, if n to the t is highest degree term in the numerator, n to the r, highest degree term in the denominator, if I find that ratio, that will tell me what the limit is approaching. We could have looked at that here for number 7, where let's pick green. If I look at these two highest degree terms, then I can think of, well, what is the limit as n approaches infinity of 10n to the fifth over n to the fourth? Well, 4 of those cancel out, all of these cancel out, and we get this line here. So it gets us to this point quickly. That's a good way to check, but I'm expecting you to show this process. And there we go. So use the shortcut for checking. Use this longer method to actually show the process. And then we're on to check your understanding questions. So 8, 9, check your understanding. Next page, 10, 11, 12, also check your understanding. Here we are just going to do whatever we can. Any method you can imagine to find these limits, good luck. Once you finish those 5 questions, I'll have you restart the video. But for now, pause it and start with question number 8. Well, here's my process. Again, my highest degree term in the denominator is n to the fourth. So that's what I'm using the reciprocal of as I multiply into numerator and denominator. My limit will simplify down to a negative n. So as n approaches infinity, negative n will go to negative infinity. The limit doesn't exist, but it's approaching negative infinity. Question number 9. Now my highest degree term in the denominator is this negative n to the sixth. So that's what I'm using to multiply the reciprocals into numerator and denominator. And then we have this interesting thing where all of my terms in the numerator have an n in their denominators, so all of those go to 0. Well, it's okay if my numerator goes to 0, because 0 over any number is 0. And there's my final answer. On to number 10. I don't know what you did for number 10, but I built myself a table. And I said, as my n value gets bigger, what's happening to this negative 2 to the n? Well, the size of my numbers gets bigger, but it bounces between positive and negative, so we get the sequence that's diverging. So it's not converging to a value, and so we'd say that this limit doesn't exist, which is what I have up here in black. The next one. As I have my n values increasing, my term value bounces between a positive 1, positive, negative, positive, negative. It does not converge. I wouldn't say it diverges. They're not getting further apart. It's just not converging. So we'd say the limit doesn't exist because it's not converging to a finite number. Then as we look at number 12, what's happening? Well, here you can see I've said it's equal to 0 because what's happening? As my n gets larger and larger, my term values, even though they're bouncing between positives and negatives, they're getting closer and closer to 0. It's approaching from the positive side and the negative side, but as the size of these numbers gets smaller, the whole thing is approaching 0, so we'd say it is converging to a value of 0. Well, you may have guessed this based on the sequences that you looked at, the geometric sequences that you looked at in grade 11. Although some of you may not have done them because you were quarantined at home and that might be something that you skipped. But here's what we find. If I have r to the exponent n and my exponent is approaching infinity, then as long as the size of my r value is less than 1, now to help us understand this, I could write this. This is the same thing as saying that my r value is less than 1 and greater than negative 1. So it's in between negative 1 and positive 1. So my r value, if it's in between there, then the limit of r to the n will be 0. And that we saw demonstrated in our last example here. The r value was between negative 1 and positive 1. Its size was less than 1. And we found that it converged to 0. Here, this was equal to negative 1. And notice in our statement here, we have less than, but not equal to 1. So it has to be less than 1, the size of that value. And there we go. That's all that we're going to be learning in Chapter 1. Do some practice, do some review, and we're ready to assess and then move on to derivatives in Chapter 2.